Intermolecular physical forces. Now, what does that mean? In the universe, there are three interactive forces. Nuclear, chemical, and physical. Well, if you stick around for some Chem 2, we will certainly look at some of those and how the energy relationships evolve from interaction of nuclear particles. And these are in the order of 10 to the 6 kilojoules per mole kind of issue, just as a reference number. The atom bomb, hydrogen bomb stuff. Then we talk about chemical interactions, which is nothing more than chemical bonds, which is in the order of 10 squared to 10 cubed. Depending on the types of bonds and the organization and stuff. But a physical bond is a very weak electrostatic interaction. On the order of 0 or 10 to the minus 1 to say 1.0 kilojoules per mole. Very weak, easy to break. Now, when we talk about physical intermolecular forces, these are the forces responsible for states of matter and changing states of matter. And they come in three classes, which we call dipole interactions, hydrogen bonding, and London forces or dispersion forces. First one in the list is the dipole interaction, and it needs exactly what it states. It needs a molecular dipole. Now, what does that mean? It means an asymmetrical distribution of charge such that one end of the molecule has a partial positive and the other end has a partial negative charge. Asymmetrical, just one S. to illustrate this as a non-dipole, say methane, we know that it has a tetrahedral geometry and it has a symmetrical distribution of charge along the bonds associated with it. Therefore, we can associate this, say, with just looking like a big blob of negative charge floating around, and everybody's the same density. However, if we take something like chloromethane, which has a chlorine substituted for one of the positions in the methane instead of all hydrogens around, we have the same structure, but say you have a chloride at the top of this lousy looking Cl, or whatever, this highly electronegative, and then you have your hydrogens here, here, and here. Well, because of the strong electronegative nature, the electronic structure is displaced toward that chloride, and you have a partial positive charge on that end, and the center, or this portion of the molecule, let's not make it a center, this portion of the molecule would carry a positive charge. And so what you would have is, say, a molecule with a negative end and a positive end that would interact with another one, positive, negative, and so forth, etc. Now, something that has a same density, electron density throughout is nonpolar. This would be a gas at, say, ambient conditions. But only changing one element in the structure creates that separation of charge, or makes the dipole, and this is a liquid at ambient. Well, so that's the simplicity of dipoles. There are many dipoles due to this electronegative separation, and you'll have liquids at room temperature that otherwise, without that dipole, would be a gas phase substance and could even move into solid phase substance. Sometimes it's listed as H bonding. The definition of hydrogen bonding is very important and is also very wordy. But in writing it out, I will draw it and illustrate exactly what you need to look for and some of the implications of what the dipole-dipole structure of this is, why it's important. Okay, hydrogen bonding is an electrostatic interaction between hydrogen and a very electronegative element. specifically nitrogen, oxygen, or halogen. Chloride, chloride, bromide, that kind of thing. Such that, as this is continued, the hydrogen in the bond, in the physical bond, is chemically bonded I should say also chemically bonded to nitrogen, oxygen, or halogen. Consider water. We've learned in the geometry section, water has a bent angular geometry like this. Well, because of this asymmetrical distribution of elements in here, it's also a strong dipole toward the oxygen, such that if you took a line of symmetry and split it in the middle, you'd find the oxygen end to be highly negative in charge and the hydrogen's end to be highly positive in charge. And that's the nature of water. Now, when water interacts with another water molecule, the positive end, or the hydrogens, you might say each one's carrying a positive charge, and these electron pairs are your negative charges right here, interact. This has to interact with an electronegative oxygen. See, that's negative, positive, negative. And I'll put little dotted lines like this, which is the electrostatic interaction. And this represents the hydrogen bond. But one other requirement is needed in that structure. This hydrogen that's in the bond itself must also be chemically bonded to oxygen, nitrogen, or a halogen. These are the two implications of dipole and hydrogen bonding, or dipole interactions in general. The boiling point is increased for the liquid substance, as well as the vapor pressure is significantly decreased. To show you this, I've got a diagram from Ebbing's 9th edition, is in the 10th or whatever, if you look it up. And this is really a classic diagram that's used quite often in talking about these kind of topics. We'll start over here with this one. Well, let me see if I can make it a little bit smaller. Yeah. Okay. Starting right here with water against hydrogen sulfide. Okay. And here's one with methane over here. One of the first things I want you to notice is water has an 18 atomic mass unit formula weight. 16 plus 2 is 18. Methane over here, pretty close to the same weight, 12 and 4. 16, 12, 30, 40, 50, 16, here's 18. The the molecular weights are approximately the same. However, this one has a boiling point that's below 160 degrees Celsius, whereas this one boils at 100 degrees. Why? Well, of course, the hydrogen bonding plays the big part. So there's an strong interaction between hydrogen and the oxygen, hydrogen bonding in the water, whereas there's no interaction at all between the molecules of methane. And so in order for methane to be put into position like in the liquid state, high pressures have to be applied to that substance and low temperatures, and then it's very unstable, and even that condition, release of pressure or increase of temperature, causes it to move into a phase change very quickly. But water, because of its asymmetrical distribution of charge or hydrogen bonding, maintains a very high boiling point. Now, it is the interaction, say, hydrogen with nitrogen or oxygen or halogens that constitute the hydrogen bonding. Once you move away from that, the boiling point is a size of central element issue. So what I'm saying now is, like water, while it's 18 atomic mass units, hydrogen sulfide jumps up to 34, but it has a very low boiling point. And it's a size issue. Now, this is an electrostatic on water. This is the size of the central element. How do I know that? Because in the same group, there is sulfur, selenium, and tellurium. And as the size increases in the particles, so does the boiling point. That's the objective of this diagram, is to show you that in a binary hydrogen-containing structure, the boiling points will increase because of size after the water, and because the size changes. And you can see this over in this one, probably just as clear. The HF and ammonia demonstrate hydrogen bonding, was showing very high boiling points relative to the other substances on this graph. Whereas, like I just mentioned a while ago, methane doesn't have any charge interaction at all, so it's very low boiling point. But after the nitrogen, oxygen, halogen interaction, it's a size control. Well, actually, it just goes through chloride, because, see, chloride's a bigger molecule. You don't have that extreme hydrogen bonding here. But you go up to HCl and then HBr and HI. Those are size variations. Here is a 3-hydrogen series. Instead of ammonia hydrogen bonding, it drops to BH3 because of size. And then as compared to arsenic, trihydride, and so forth, it's a size issue. Hopefully you can see that in these diagrams, and that is a question on the exam. So you're comparing boiling points of hydrogen-containing structures, binary hydrogen-containing structures. Who has the higher boiling point? Well, it's always water or ammonia or hydrogen fluoride, because they demonstrate the highest degree of hydrogen bonding in those structures. Now, another one is over here, and here's the hydrogen bonding that I was showing you a minute ago in the water. But if I have an OH group on a structure, it is typically, in an organic structure, it's typically called an alcohol, like CH3OH is methanol, or CH5OH, yeah. is ethanol. Well, that OH group in there contributes to the hydrogen bonding and bumps up the boiling point significantly. Yeah, see these right here? Here you got an OH group, you got 3 OH groups, and here's a methanol group right in here. Well, these OH groups all contribute to hydrogen bonding and bump up the boiling point significantly. That's too much. Get it on there. Which of the following compounds is expected to have the lowest vapor pressure? Number 54 and 55. Which has the lowest normal boiling point and which has the lowest vapor pressure? Remember I said there are a couple of things that are affected by hydrogen bonding or any of the dipole-dipole interactions. That's vapor pressure and boiling point. Because boiling point depends on creating a vapor pressure necessary to reach atmospheric pressure. And so if you have an interaction between molecules that prevents them from evaporating, then it takes more energy and it's harder to get into the vapor phase. You have to have a lot more energy, higher heat, or higher boiling point. So which of the following compounds has the lowest normal boiling point? That would be something that would evaporate very quickly. So that creates what we call a high vapor pressure. So molecules that evaporate quickly have high vapor pressures. Try to get that straight. And low boiling point. High vapor pressure, low boiling point. Alcohols, ethers, for example, boil at very low temperatures, but the alcohols jump up into much higher temperatures in the boiling because they have hydrogen bonding in them. And then a low vapor pressure, something that inhibits evaporations, larger molecules or high interactive forces, has high boiling points. Like that. So that little relationship is very important in making decisions on the exam tomorrow on some of those questions. You want to get all of those. These are easy because I don't even have to learn 2 conditions. Okay, so you look at these molecules. Here's one on the end. Nitrogen has a lower electronegativity than does the OH group over here. The higher the electronegativity, the greater the hydrogen bonding effect. Both of them demonstrate hydrogen bonding in there. But the OH having a higher electronegative effect would have the higher boiling point because it inhibits evaporation of the molecule. Now stuff like this is a dipole-dipole. Dipole is a step down, so to speak, in electrostatic interaction than the hydrogen bonding. So this would have the lowest boiling points, a lower than these 2 here. And then here's one that's a carboxylic acid. Boy, that's got a lot of electronegative character in it. I'd say that one would demonstrate a lot of hydrogen bonding also. I didn't notice this CO in there. What this is this kind of structure. And so if you have another one out here, like that, that's going to be a very strong. So I take that back. This is the highest boiling point right here because there's a lot of structure in there. I would say this one, in looking at hydrogen bonding, all of these, this one has an OH group in there. That's a group that has an OH side group on it. Anything that has an OH group in it, or an ammonia group in it, would have hydrogen bonding, which bumps the boiling point way up in the context. The only one in here that doesn't have hydrogen bonding is this one with the fluoride on the end. It's a dipole-dipole. So that has the lowest interaction. So you got to look at the molecule and look for the OH groups. OH groups say hydrogen bonding big time, also the ammonia groups, but they are a lower electronegative nature. So OH groups first, high boiling points, and then halogens, dipoles next down boiling points. Let's see what this next one. Here's one that's the molecules are all different. Here, this is a good one. Lowest vapor pressure would be the low particle-particle interaction. Something like these chain groups, the longer the chain, the greater the interaction. We haven't talked about the London forces, but this is 4 carbons against 3 carbons. These, if you had a bottle full of this, 4 carbons, you're talking about the chains interacting with it. The longer the chain, the more chain-chain interaction. So this has a lower vapor pressure than this one right here, because there's only 3 carbons in that one. So this one would evaporate easier, making this a higher vapor pressure. Now this one has an OH group in it, hydrogen bonding, so that would be the OH yields hydrogen bonding, and that yields a low vapor pressure. Now this is a dipole. Actually it's this. It's like water, but it doesn't have any, it's a partial negative, partial like that. It's very weak dipole, very, very weak, and evaporates very easily, but as far as the lowest vapor pressure, it would be the ethanol. And the OH, stronger. The lower the vapor pressure, the higher the boiling point, because it takes more energy to kick the molecules into the vapor stage because they're held into the liquid. Highest normal boiling point, we looked at these. It's always the hydrogen fluoride. That's a small, highly electronegative element. Remember the graph that I showed you a minute ago? Has the greater electronegativity. Well, anyway, I need to go through London forces. Oops, wrong way. Sorry. Now, focus. The third type of physical force is the London forces. The London forces are electrostatic induced forces called induced dipoles. Under high pressure, and low temps, molecules and elements form dipoles and transition into liquid states, liquid and or solid states. For example, argon is a noble gas with a symmetrical distribution of electron density. But if it is forced, high pressure, low temperature, close to another argon element, and this is true for the methanes and the symmetrical others. This is simpler to explain this way. This will go to an interaction between those two where you have a very little number of negatives on this, a higher number of negatives and a low number of negatives on the other side, with a center, and then you have a low, and then high numbers. And what it is, the positive charge of 1 interacts with the relocation of the negative charge. And this creates the induced dipole, or forced dipole, which goes toward the more negative side of the structure. And that's liquefaction of nonpolar systems. So if you have hydrocarbons, what we call nonpolar hydrocarbons, such as, say, methane, ethane, propane, etc., like that. These have to be liquefied by high pressure, low temperatures, like that. But as the chain increases, increasing chain length causes the structures to favor natural liquefaction and solidification. For example, get up around 1, 2, 3, 4, 5, 6, 7, 8 octane. Then this would be a liquid at ambient conditions. Or if you get into long chain waxes, that's the symbology for polymer repeating chains, like this, wax. These are solids, even though their structures are nonpolar in their nature. It's the long chains interaction that favors liquid and solidification. Now, one little extra notation here in the larger structures. If there is a group, a side group in this chain that breaks up this interaction, then that lowers the potential for solidification. For example, you got a long chain and you put a group on the side of it like this, well, it's going to have a hard time getting into the connection. So the London forces just aren't there. Waxes melt very easily, as you know, because while they're long chains, there's a weak interaction between the surfaces. Okay. Properties of liquids. When we talk about liquids, of course, they take on shape of whatever container they're in, but they also have a thing known as surface tension and viscosity. The term surface tension The easiest thing I can give you is spreadability. 1 over spreadability. Something that has a very thick character is difficult to spread. The molecules are held together. So high surface tension means strong particle-particle interaction. So if you have increasing surface tension, you have strong forces and it's hard to spread. Syrup, it'll spread out but it'll hold together. Surface tension is responsible for making bubbles go into circles because all of the interactive forces are working toward the center of that liquid system. That's enough. The other term, viscosity, is pourability. Might reference high viscosity as pour flow. In other words, it's like thick hand soap or thick dishwashing soap. Something that has a high viscosity has a thick nature. Syrup. Those. Water has a low viscosity. Matter of fact, water is the standard. The pourability or the flow of water is other substances are compared to the flow of water in what they call a ball drop test. If you want to know the viscosity, it's called a relative viscosity. Take a graduated cylinder and fill it with the water in one and liquid, unknown liquid, liquid of interest, and you drop a marble in it. The time that it goes from top to bottom is what you're referring, and you compare delta T for the liquid of H2O, and it's called a relative viscosity. It's 1 to whatever. It takes twice as thick as water or half as thick as water. And it all revolves around particle-particle interactions. They come in 4 flavors. Okay, solid. We have molecular solids, such that you can isolate an individual molecule. One structure from the other. Let me see. I've got dry ice. CO2 solid, dry ice is a individual structure. Ice itself, H2O, in solid form, whatever you solidify, molecules that can exist, organic molecules exist in solids. The other one is metallic solids. And these interact in terms of what we call metallic bonding, or sea of electrons. Gold, silver, copper, and so forth are highly ductile, and they're continuous in their characteristics. Ionic solids, salts, are 3D structures based on 7-unit cells. Now, I don't know what your future holds, but in ionic salts, many of you have seen crystalline demonstrations and seen salts that have been crystallized. Well, these come from 7 basic structures. Now, I'm not asking any specific questions, but this is a note that you might find useful in the way I present it. There is an acronym for the base crystalline structures that generate the different salt crystals. C. Tom Hart. That's like Roy G. Biv kind of thing in the colors, but these are 7-unit cell structures that make salt crystals. Cubics, triclinic, no, let's see. Oh, God. I don't remember. I can't remember what that one was. Okay, just want to illustrate this, that's it. And some of you may go into crystallography someday. And let me show you what they look like, and that's all I'm going to do. Okay. C. Tom Hart. Okay, I don't know. Some of you may become material engineers and need that, but that's what they look like. Okay, and it's a classic acronym. C. Tom Hart. There's your cubic structure, and there's your tetragonal, and there's orthorhombic, monoclinic, hexagonal, and after that, you go through some bunch of analysis to determine from the X-ray diffraction patterns what that salt is and how it's characterized as a salt in that with that unit cell. That's it. After that, good luck. Okay.